Hi everybody, and welcome to my intro talk and demo about machine learning for automated. The uh, aim of this talk is to show you what automated mapping using machine learning is, and using a science case that is meaningful. So try to give you a hint how to apply those tools to the science case or science goal that you have in mind. This is my tentative plan, so I will try to introduce you briefly to the target or the scientific target of this talk. And it's not necessary to look at it and to hear about it, but it's interesting to know why we are doing that and why we get there where we are. Then I will explain a little bit how we can get the data cube that is the input of our data analysis. It's not super essential, but if you get a hint how I got the data, then you can have a better idea why I do such things like filtering data or trying to get less noise and so forth. So it's useful, but it's not essential. If you want to just get a gist the idea about how handle the data and analyze them, just skip to the part 3. And so the actual work on data. It will be a mixed part between presentation and the book. I will go switching back and forth between the two. Try to be as clear as possible. So if you have any question or something is unclear, just email me. I've seen the mail in the first slide, or try to copy the email from this presentation. If you follow me and you find any problem, please notify me or open an issue on GitHub. I'll try to fix this as soon as possible. The last step will be to compare what we reproduce this talk or with this demo with other products. So stuff that were done from other user or data that are coming from models, or try to compare our result with other things to see if we objectively find something. The last important thing, all the underlying text in this presentation are hyperlinks that I put there for you to get more information about the topic I was talking about, and not to go too deep into the technical details. I just refer to external source to show you just to show you the essential part. Okay, first background. This work I'm gonna show you is based on the chapter of the book that I wrote for this book about the machine learning for planetary science for Elsevier last year. This is the title. You have the DOI and you have everything, and you have even the GitHub repo where you can find the notebook. Most likely I will put also this presentation as PDF there. It's a nice resource. And you should have from the Winter School links where you can find this video recording. So this is the table of contents. So we are already started. So we have a general introduction. Then I will give you some background about Mercury, planet, and the mission that get there. So where we get the data, and then how to build and work on the data that we produce. The different steps. So we build the data set, so the data cube. We decompose or we compress the feature, and we project those multidimensional feature on a map, meaning that we have 2 coordinates and a third value to visualize on the map. And then we apply a so-called clustering technique that will put pixels together on the surface, link it to a similarity function that we can define, and we compare with other results, and then we see a short review of the results of this work. We can say from the work that you do. For the one who want to follow with the notebook, those are the necessary steps that you need to follow me. So first, you need one of those Conda, Mini Conda, Mamba, or Mini Mamba installed. I suggest Mamba a little because a lot faster, but Conda is perfect, or Mini, whatever you have. The option is to go, okay, I forgot that naturally you have to clone all the repository and then go in the root directory and run the first option to run the make create environment, and we'll do everything for you. Look for if you have Python, you don't have you have Conda, whatever. If you don't want to use this or you're uncomfortable, you just run this command to create a new project, change the project name to the project you want, and install everything that's in the requirement file. That's all the Python necessary Python packages. Or as a third option, you create environment manually as you wish, and then you can just run pip install -r the requirements that are listed in the requirements file. Then the second thing is that you need the data. You can run this command here. You also have it in the notebook, and you can get the data that you need from Zenodo. It should be a couple of hundred of megabytes, but it's not amazingly huge. It's a big JSON file that I will show you how it is. So it's a collection of spectra and polygons. So with this cleared, let's start with the background. So the target of our investigation, so the target of the data we will use in this talk is Mercury. So the closest planet to the sun, one of the smallest terrestrial planet, and it's really an extreme among terrestrial planets. It's the smallest, densest, the oldest surface, and one of the largest daily variation in surface temperature. We see that in one of the last slides. There are a couple of interesting parameters you can see listed here. So if you want to go deep down this route, you can go to even the Wikipedia page is nice, or NASA page, or ESA page, background material. The point is that we want to understand how Mercury was formed, what is about its surface, how the surface getting the shape that we have now, because it's one of the really interesting end member among terrestrial planets. So if you have the Earth in the middle, so habitable and nice planet for us, then you have on the other extreme, you have Mars, you have Venus, and you have Mercury. That's an outlier, different point of view. So the first, no, I'm not talking about terrestrial data, so telescope data. I'm just talking about remote sensing data. One of the oldest that we have are the first flyby by the Mariner 10, or in the 70s, and we got pretty huge surprise at the time. People were thinking that the Mercury was not that interesting, and we got a lot of data. I mean, not nowadays standard. I guess there were a couple of kilobytes anyway, a little bit bigger than that, but not huge. But the second encounter with the planet was with the Messenger mission that had a multi-year mission around the planet with a suite of different instruments, ranging from laser altimeter, spectrometer, camera, magnetometer, different things to investigate different parts of this complex system as a planet. One of those is the source of the data that we're going to use. It was the mass spectrometer. So if you follow this link here, you can see a little bit more information on the mission. Going on, we are doing that because I, with my group, are on board the coming to Mercury mission, the Bepi Colombo mission that's already started. Already at the time when Tolkien had a flyby around Mercury, and we are the one that we are build and test and operating the spectrometer on board this mission. So we need to have a background on the spectrometry on this planet to have an idea what we are going to look when we get there in the future. So this is my work episode. So our hypothesis is that the surface composition information can be derived from spectroreflectance measurement that we have on the surface. Which kind of analysis we're gonna use? We're gonna try to identify and characterize spectral units from orbital observation made with this mass spectrometer during its primary mission. we're going to apply the so-called ICA, so the independent component analysis, and this will be used to decompose or compress the data. So we have several bands and we're going to compress in a smaller space. All of these links are further explanation about those techniques. Then we want to project those compressed data set that's not yet small enough to be visualized easily to 2D. We're actually going to produce a map using this UMap algorithm, and we're going to apply on those two components an unsupervised clustering techniques called hierarchical agglomerative clustering. And we're going to compare those results with output from different sources. So this is the first step. As I say, this spectrometer, this instrument, is not an imager, like most of you is used to, I think. It's producing a single pixel per observation with a lot of spectral bands. So we're not going to have 3 for the typical image with color. We're going to have more, several hundreds bands. In this case, I'll show you on the right, you have something like around 10,000 spectra. Each single polygon here, the small one, the big one, a polygon measured, a single measurement of the instrument. And on the left, you have the area that we designed to be interesting for our study. So we just have an algorithm that we are using to select the data on this polygon. And we can average them. And then here on the right, you can see that we have average spectra of this red region. So red polygons are the average, are the average of the outside region. Then you have spectra of the internal of the crater, the slide on the side, on the central peak, and so on. Applying the same idea, we produce a rectangular grid on a small portion of the planet. And you can see here all the observation. And in this zoom area, you see that on some particular spot, you have a high density of observation. In other part, you have the observation. What we do, we use the singular polygon here, so this square, as our the region of interest, and then we extract all the polygons that fall in this smaller pixel, and then we can average them and produce something that's close to an image. So we have a multi-spectral cube, and we can apply this on the whole surface. You can see here in different wavelength that you see some difference on the surface. So different wavelength, you have different spectral characteristics showing up. So if we apply this on the whole surface, we get different layer at different wavelength. In this case, the Z direction going into the screen is the spectral channel. You can see here our final data cube, we have 354 different layers. So it is like an image of several hundred layers. And the X and Y direction are actually latitude, longitude and latitude. And the grid size is 360 per 180, so 1 degree per pixel. Obviously, you see some part here on those calculated images that are not transparent because there are points on the surface where we don't have any observation, so they are transparent. So this schematic is useful for us to illustrate which is our goal. So we have this huge data cube. So it's actually 360 per 100 per 300 something. That's a round number. And we want to compress all this information and extract area with similar characteristics. You see on the right here, when I have a map, and each pixel is linked to other pixels that are similar. Similar being in a metric that we can decide. In this case, we use 3 different colors to depict 2 different areas that are similar in some way. So how can we go from this left panel with a huge data cube to the right panel where we have just 1 layer? This is actually what we're gonna go now. So let's start. So first thing is to unravel this data cube, and instead to having 3 dimensions, we're gonna put in a tabular form. So we have all the spectra on the each row is 1 spectra. Different color here are the different layers you see on the left side. And on the X direction, you have the spectral channel. So you're going to have 354 different channels. In machine learning, normally you call this direction, the x direction are the feature, and the other direction, the y, are the sample. The idea is that per row you have an observation of something, and this something is defined by different feature, different column, define different characteristics of this sample. So this is the whole workflow that we're gonna go through. So we have this data matrix in tabular form, is mentioned here. We're gonna compress using some decomposition. I told you before that we're gonna use the ICA, but if you in the future you're gonna meet also for sure the PCA, the principal component analysis, those techniques are similar, different background, different assumption, but they work in a similar way, and they're gonna give you a representation in a smaller space of your data. So starting from this more than 300 feature, we're gonna compress those to 4. Then we want to apply the so-called manifold learning, and we're gonna project this 4-dimensional space in a 2-dimensional space. 2-dimensional space is really something you can plot on a 2D plot and have an idea how the data are in the data space. We're not talking about geographical at this point. And then having those things, we can apply a unsupervised clustering algorithm on top, and then we can have per row different color that are telling us which cluster each pixel belongs to. Okay, so and then as a last step, so I compressed the previous slide, just those two. So we have the data matrix, we do all this work, and then we get there. So we have per row different pixel, and we can take the location of each single spectra and plot the pixels on a real map, so latitude versus longitude, and we can start to show if we have the map start to show if we have some current structure, and then we can overlay on real maps, like really photographic images, to see if this correlate with structure, like in our case craters, ridge, or I don't know, different geomorphological structure or other data that we show you. So those are the first image from the paper that I showed you at the beginning, and we are going to produce something similar to this image. Some of those algorithms are randomly initialized, so they will be a little bit different from what I put in the paper, but the end result should be the same. So you see here, you're already seeing how the data look like. So in this case, there are some data on the Kuiper crater, one of the very interesting spot because it's due to its high albedo, is thought to be one of the youngest crater of Mercury. And can you see was target from different observation of this instrument. And on the right, you have the global data cube. In this case, I'm showing you the reflectance at 700 nanometer. You have an idea the data shape we are dealing with. So the first algorithm we're gonna apply is the independent component analysis, and I told you it's a way to decompose the data. And the classical example is to the cocktail party problem. The idea behind this, you have a cocktail party, a place where a lot of people are talking at the same time, and you have different microphone recording everything. At the end, you have different signal, and you want to decompose in a way that the different component are the talking or the sound for each single source of person. You can do this. Just let me switch to the book. So if we go to start of the notebook, okay, we have the title of our presentation that you're reading. That's the title of the paper that we have. Those are the classical imports. You can go on. I just filtered out some warning that were coming from plotting routines. Here there are some functions that I defined to do plots and other things that are simpler. I'm not gonna tell you about this. Here is where you can get data. You should already have this. Then we create the wavelength grid. Those are internal definitions from the dataset. The name of the input file. It should be the same. Then load the input file, define it as a data frame. In this case, it's a GeoPandas data frame, so it's a ready geographical structure. So it's a table data with attached CRS, so the coordinate system and everything useful. So we extract from this big data set even the spectra that are already in, so each pixel with all the bands, and then we create some auxiliary column X and Y to give it a bit more freedom to plot. And so in this case, you see we have the original spectra are exactly 360 per times 180, so they're all the pixels, but a lot of those are not there because they're transparent in the previous plot and they're actually filtering out. We have more bands here, but I'm gonna cut here to a little bit smaller because the edge of the detector in this case are a little bit noisy. And you can start to do some plot. In this case, I'm plotting the number of, not a number, per wavelength and per. So I can show you, this is the data frame with the geographical data inside. So they're actually just the index of the spectra, the definition of the field of view, so the spectra where it was measured on the surface, and then you have the centroid, so the center of this polygon, the X and Y, there are the longitude, the latitude. So let's go on with some other. This is the spectra data frame. So you have the same index as before here, and you have as a column names are exactly the wavelength. Those are resampled. So those data were gone through a little bit of work from me, so not directly from the original data source from NASA, because there are some binning and other things that I prefer to do to resample everything to have simple wavelength, and it's working wonderfully. So let's plot something. So let's plot the distribution of the old data. Will take a while, takes a while, and show you we are here. And then after a little bit of plotting, we're gonna go back to the dimensionality reduction we were talking about into the presentation. This function here, it's used to save the plot produced here, and in this case is controlled by this Boolean parameter that now is shut off to not overwrite the data every time. You can change it at the beginning of the notebook, and you can actually save the plot for yourself. Time. This is due to the histogram. Stop it. Stop it because it's useful time for this. This is a spectrogram. Actually, it's actually all the spectra plotted as lines, and we can visualize. Yeah. So on the X direction, you have all the spectra, and the Y direction are actually all the way. You can have an idea how they vary. I will show you some better play. We have the dimension of the different data frames you're working with. So the original one, spectral data, and the spectral data without not a number. Then we can plot something. We can calculate something. In this case, we set into wavelength. So those are wavelength in nanometer, and we calculate the ratio between those two. And this we store in this data frame in a column called ref. But it's a little bit a trick. So let's do some plotting. Finally, so you see here, we sampled. There it is. Here we sampled 25 different spectra. That's chosen among the one without not a number, because even the spectra are noisy. And you can see here relatively easily, we create a two panel with plots, subplots, and we plot first all the spectra. With a little bit, it's a trick because I just plotting with the Pandas API, but because I put the actual X values into the column and I translate it here, that way taking the index. In this way, the index are the column and the X are the wave number. And I think I can even ask him to make the mean on all the data that I have here. And I can overplot, and you see here you have the average spectra here. And we're using the same index to take out the location of the spectra, and we're using as color the ratio that we calculated before. Pretty easy. This is done with Matplotlib that you maybe are used with. I'm gonna use here another program package called, in this case it's Bokeh, but it's used by called by all of you. Another nice package. So here we define the first plot, multiply by the second plot, the average. And you actually, we can make a little bit. And you have the data here. And the nice thing about Bokeh is that it's interactive. So you can actually zoom in. Relatively easy. You can explore the data. You can actually disable some lines, and you can here go back or some particular region. You can even cross-link the two, but I didn't do this work. Something that you can do if you want. So then on, and we can plot the, I hope it will be nice. Yes, those are the data distribution at 3 different wavelengths. As you can see here, I defined the 300 nanometer, 700, 900. They put everything together. You can see how the I'm not wrong, this is the first one. So this is the 300, then you have the 700, and then the 900. You see that there are picked different values, but the data distribution is really close to a Gaussian per wavelength. That's nice. So then we load some background images. And this the background image is a Mercury global backplane that you can use afterwards to overlay our results. Here I'm showing you one of the column of the spectral data frame, and you see that we have some data here that are not a number. So those are the one that I normally filter out. And we can show you how to combine the two. Okay, this plot are really bad. I don't know why after I update everything, the Matplotlib extension from all of you, it's completely done. Didn't achieve a better representation. This bad, but if we use the Bokeh extension, it's nicer. Yeah, here. And we actually overview relatively easy the background, and then we plot this spectral data frame we have before. And as before, as I added nicely, we can zoom in, zoom around, search for something here. So pretty. Then start to learn something about this data. So let the machine learn. So those are again the data size that we have, and start with the machine learning. Here you have even part about the PCA that I will skip. But as I told you, conceptually, it's relatively, the flow of the data is similar to the ICA that we have here. So the ICA will try to decompose your data to a smaller dimension. This means that we're gonna try to find a new base to describe your data. And so switching from this 300 dimension to a smaller, in this case, we call this number K. You can see here our aim. So I already know the result. It's gonna be, this K is gonna be 4. It means that we are gonna coming from 50,000 different observations with 300 dimension. We're gonna describe those things in a base of K vectors that are maximally independent components. Those are this data in the final result here in this equation. And we have for each one of this component the coefficient describing original spectra. So for example, one original spectra will be described as a composition of this 4 or K number of spectra that we define to be the maximal independent components for this particular decomposition. Each decomposition will be different because, as I told you, the initialization is randomized. So that's why the result here will not the same as the one in the book. So how are we gonna find this number K? We essentially, in my case, I decide just to increase the number starting from 1 and going up. And you can see here the definition of this distance. You take the norm of the original vector minus the reconstructed one, and you compare it with some number. So when you go below some threshold that define in this case, the noise level in your data, you are sure that you have this stop to describe significant feature, but you start to go into describe noise. So you have here a graphical representation and matrix representation of this difference. And actually we can produce this plot here, just going back to our notebook, and so here we produce a plot where you can see here for after this 4 we have a reconstruction error that is higher than the typical number for the noise, and you can even produce a similar plot to the one I produced in the paper. It's code. So okay, actually we compute the ICA for different number K, so we reconstructing more and more error. And we fix here with 4, so we want to have 4 components. And we have the size of the original data. A matrix is giving us the coefficient, so actually those are the spectra, sorry, and this S here are the coefficients. So, okay. We can even plot those coefficients on the surface because each single spectra, each coefficient, it comes from the decomposition of the original spectra. It means that we have the coordinates for each original spectra. You can put on the surface and see, okay, this first component here is giving some structure, but it's a little bit noisy. But this one, for example, is a lot more coherent, and we have a higher redder region here. So in this case, I put a scale where we have higher is red and bluer is lower. We go back to the presentation. We can see here, those are the data that we have in the you can see the 4 components. We're different in our case now, and those are some scatter plot of the components, and those are the geographical plot of. So back, and we let me so yes for you. And okay, this is another part. It's the third part here. That is actually, so we already done the position, and we're gonna go on with other part. That's the manifold learning. Manifold learning is at the end, it's a representation of your data space. So your manifold, it's a structure in a higher dimensional space. We project to a smaller dimension, and this is done with some highly complicated. I cannot Okay, I understand how it works. Really hard to explain in a very small time. Actually, using some topological, so it means using tools that give us an idea of similarity of the space. We produce a space in a lower dimension, it's a two-dimensional space, and we're playing with the parameter. We have different representation of our original data. So all these plot here are different. All this algorithm, we can produce that again. Yeah. When we do this step, we have gone another step further, and we compress our two dimension. Okay. Just briefly. We load some cached data. So those methods are really, really expensive in CPU and calculation. This is another manifold learning method that you can use if you want, and use the UMAP. And what I've done is actually run different parameter. This parameter means different stuff. So put a little bit more emphasis on local structure, on global structure, how big are the neighbors, and different things. Each run produces different shapes. I put everything together, and at the end I chose to use this one as out. And this is how we projected the space, and this is cut up. Next step is the classification. Classification means, given all those feature, how can we put them together in a way point in the same class are more similar than the point in here. You have foundation of scikit-learn that we're using here, different data, and how different algorithm works on this different data. You see here the one that I got agglomerative cluster here, and how it works on different shape blobs here, circles here. One important point here is the preprocessing. Doesn't mean reshape your scale part of your feature to be similar. In this case, I'm using a robust scaler. You can look into documentation. The essential point is when you have unbalance, you have one feature going from 0 to 0, 1, and the other feature going to billion. Big one will drive everything. So operation of one in the big one will be completely a one data unit in the big one will completely obliterate each other variation features. So it will be driving everything. If we scale everything to, there are different ways to do that. You can do with this. It depends on your particular data of outliers, some other distribution of your data. Then you scale the data so that all these methods in scikit-learn work the same. So you have this algorithm, you can fit with some data, and you get back actual fitted function algorithm, and in this case I put in the name that we can use. So it will take a while. After that, I scale the data, and then I pass here scale data where we wanna actually classify them. For the classification, I decide to use the agglomerative clustering here. Cluster those methods, there are different. The method I showed before, there are different kind. We are looking at agglomerative clustering where you explicitly ask for how many classes you wanna. Stuff like k-means, even you have this. And other algorithm like the bbscan or Gaussian mixer or other, you don't define how many classes you wanna get at the end, but it's actually coming directly. Here you have, if you wanna play with other algorithm, you can comment this part and uncomment one of those. You have here ready for you the k-means, for example. Yeah. Let's see, same. It asks for 2 different classes, but for example, bbscan, you don't define how many classes, you define some parameter giving you how it's gonna classify everything together, and it will change the number of classes you got. We go back, calculate. You see that we gone from here to the hierarchical classification, hierarchical clustering that actually creates a hierarchy. So it's like a tree. This plot here is called a tree. And you can cut this tree at some point. Big step here, big leap means that on each node you define a cluster here, a group. And this big leap means that those nodes defined here are totally lot different from the one here than in this small step. So we choose to stop here, and we have 3 cross points that are our 3 classes that we ask. So, and actually we got at this last point. So if we go further, check sometimes if finished. Yeah, okay. And we produce this. So this is a classification map. As I told you before, we put all these learned classes. We take the location of the spectrum and we put on a map. On the map, you can see that we have different classes that are geographical current, are not just noise. That's really nice. And you have the average of all these classes. We took all the pixels together, and we have the different classes, and you can average, and you see that the red one are the highest, and it's redder in the spectroscopy world, and you have a middle class here that's overlaid with average, and you have bluer class. It's light blue is the middle one. So if we go on, if we use another algorithm, as I told you, as I showed in the notebook, we have, for example, the k-means. It's widely used because it's really fast. But there are different assumptions. In this case, it's cleanly cut our data space. It's something that I don't like because I don't see any clean boundary between these two. I'm not really sure if hierarchical is working any better, but in this case, it's just trying to follow some boundary it defines based on the similarity of the points, for example. But the result, if you see here, the result, apart the color brightness, but the results are remarkably similar. So then we go to compare those results with other products, and in this case, you have 2. So in the top right, you have the user-defined map. So it was a scientist that was the Navy here that published these results, a morphological mapping of the so-called northmost plane, that are younger planes in the north part of the planet, plus the big Caloris basin that it's younger than the other parts. But this part is remarkably similar to this red region in the north. Then you have some patches here, but you have part in the south that could be related to this one, but we have to make a better comparison one-to-one. This other here is a model, so it's giving you the maximum temperature of the surface, and that's different from Earth because Earth is not rotating and spinning like Mercury. Mercury has this 322 spinning resonance, orbit spin resonance. It makes so that the day and the year are interlocked, and you have this really hot pole where you get something like almost 700 K, and then you have this going to the north. You have cooler region like on the Earth towards the poles, but you have even cooler parts here on the equator. And we think that there's a interplay between these two things. You have younger places, but you have even places with a lot hotter temperature during the day that makes the differentiation of surface with a similar composition different. So they undergo different cooking, let's say. So if we go on, we see from other work, this one for our colleagues Indu. If we zoom in, you see that we have some morphological structure like craters that are differentiated in the classification. And those are the results that I already told you. And last thing I want to show you, so the color, I'm sorry from the color, not really the same, but you see here that we have this classification that we produced before. So now it's pink, reddish, and orange. So it's totally a different color, but the meaning and the shape is really similar to the one that I showed before. So to this map. So that's everything for me, and I thank you for your attention and your time. And if you didn't understand anything, or you understand everything and you think that I did some error, just ping me, send me an email, or fork my repo and put everything even nicer, work on my stuff. So thank you very much, and bye.